section 4.1 is discussing exponential functions, and that's going to refer to both growth functions and decay functions. So we have talked about this back in Algebra 2 at length. In fact, I think some of the things we're doing this year are not really any more difficult than what we did last year in Algebra 2. Oh, just a minute. Got my smart trying to open up. Okay, so exponential functions are in the form y equals a times b to the x power. Now that's the most general form of growth and decay that I can give you. The value of the base determines whether you have a growth or decay. Rule is, if your base is greater than 1, then you have a growth function. But if your base is between 0 and 1, you have a decay function. So let's look at number 1. First of all, I notice, remember, it's in the form a times b to the x. So my b in this problem is the 1/2, and since my base is smaller than 1, I have a decay function. Now the x-intercept on growth and decay functions actually don't have x-intercepts unless they've been shifted either up or down, because you have a horizontal asymptote at the x-axis. So if I type this into my calculator, I would see, and it doesn't show you the horizontal asymptote as a line, but it does show you that the curve flattens out at y equals 0. So there is no x-intercept. And the y-intercept in this general form is the a value unless it's been shifted. So whatever the a value is without any shifts is the y-intercept. So for our problem, it's like 1 times 1/2 to the x power. So our y-intercept is at 1. I could also find that through my calculator. So if I graphed it, or if I used my table, I would see that this function, oops, that is not right. Didn't I just say it was decay? Now I would get points off my calculator, of course, to get a more accurate graph on a homework or a quiz, but basically it looks like this. The domain of any growth or decay function is negative infinity to infinity, and the range has to do with where the horizontal asymptote is located. So our range is from 0 to infinity, but notice I put a parenthesis on the 0 because that is where the horizontal asymptote is. So the asymptote that we have is at the line y equals 0. This next question is a growth because our base is 2, which is greater than 1. So if I looked on my calculator, which you could easily do, but I don't have time to, I would see that there's another horizontal asymptote at y equals 0, and there's going to be no x-intercept for that reason. The y-intercept, remember, is the a value, so in this problem the a value is a 1. Domain is still negative infinity to infinity, no matter what happens, and the range is where the horizontal asymptote is located, up to infinity, so 0 to infinity. So you have a horizontal asymptote, again, at y equals 0. This time, because I know it's growth, I am going to plug in a growth function here. Oops! Yours should look better than mine, and remember to get points off of your t-table of your calculator. This is a growth question again. It's 1 times 3 to the x power, so the y-intercept is 1. Again, there's no x-intercept because it has not been shifted up or down any, and you still have your horizontal asymptote at the x-axis. I'm going to go ahead and fill that part in while we're at it, which means my range is still 0 to infinity, and my domain is always negative infinity to infinity for growth and decay. So you will notice that if I did a better job of graphing this, the growth factor is larger, the base. So you're going to notice a steeper graph. Do better than I am doing. Now this one's kind of a trick question. 3 to the negative x power is not actually a base of 3. He's really a base of 1/3 to the x power, because remember, negative exponents take your fraction and flip them. It's x. So that is not going to change anything about the asymptote. I still have an asymptote at y equals 0. And I still have a y-intercept at 1. But now I realize I actually have a decay function with no x-intercept, and a domain of negative infinity to infinity, and still a range of 0 to infinity. So decay function, oh, do better than I am doing right now. Something like that. Okay, same idea here. They're trying to trick us. The a value is a negative 1 times base of 2 to the negative x power, which if I rewrite that in a more appropriate notation, that means negative 1 times 1/2 to the x power. So what happens to any function when I throw a negative 1 in front for its a value? It reflects him over the x-axis. So I'm still going to have a horizontal asymptote here. And it is technically still a decay function, which normally would decay down like this. However, he's got an a value of negative 1 because he's been reflected. So still, ugh, goodness, still technically a decay function. Oh, gosh, it's not supposed to look like that. It's still technically a decay function, but it's been reflected across the x-axis. So even though we can't call it a growth, simply because it's not growing without bound. So it is a decay function, it's just a reflected decay function. So there is no x-intercept, it is decay. Its y-intercept is now a negative 1, his domain is always all reals. However, his range this time, we always read it lowest to highest for the y values, so now our range goes negative infinity up to the asymptote of 0. And we still have an asymptote at y equals 0. Number 6, the base of e is really the number 2.713 blah 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 blah. It's one of those irrational numbers like pi, and that's obviously bigger than 1, so I know it's a growth function. If I graphed this on my calculator, I would see something kind of exciting happen. This x minus 2 shifts the function horizontally, and it shifts it right 2 units. So what that's going to do is not much. It's not going to shift my horizontal asymptote anywhere. I still have a horizontal asymptote at y equals 0. But one thing that has definitely changed is the y-intercept. The y-intercept used to be at the point 1, 0, 1, but everything's been shifted right 2. So that tells me this is a point of my graph. For the actual y-intercept itself, I'm going to have to use a calculator for a little bit of help. I know the definition of a y-intercept is where the x value is 0, so if I were to plug in a 0 to x minus 2, it would be e to the negative 2, which, I don't know what that comes out to, but whatever e to the negative 2 is on my calculator as a decimal, that would be my y-intercept. I don't have a calculator right now, so there you go. Still a negative infinity to infinity, and range is still 0 to infinity. So, growing, getting points off my calculator, something like this. There we go. This one, if I rearrange the order a little bit, I think we'll see what's happening. We have a negative 1 as a coefficient for a of a times e to the negative x power, and then a plus 2. So there's a lot of things that happen here. First of all, the negative x exponent means this is really a negative 1 times 1 over e to the x power plus 2. So I see a reflection over the x-axis. I see the fact that he's now going to be a decay function because it's 1 over e. And this plus 2 off to the side means that everything has been shifted up 2 units. So in this case, the horizontal asymptote, which normally was at y equals 0, since everything was shifted up 2 units, we now have a horizontal asymptote at positive 2. So y equals 2 is your horizontal asymptote, which means our range is going to change as well, but I always know the domain is negative infinity to infinity. The y-intercept would have been at a negative 1, however, everything was shifted up 2 units. So that would be right here, a y-intercept at 1. And this time we will have an x-intercept. So let me grab my calculator. And you could type in the original or the kind of rewritten translated version that we came up with. It doesn't matter. I'm going to just go ahead and type in the original. 2 minus e to the negative x. Remember, your e is second natural log button. Seems like less typing. And because I want to know where he intersects the x-axis, I'm going to find the 0 of the function. So second trace, 0, and then you're going to do this left bound, right bound jazz. And I have an x-intercept of negative 0.69. Now it's going to be a little difficult for me to actually graph it on the graph, but since they specifically asked me for the x-intercept, I'm going to So x-intercept of negative 0.69. So, and I saw from my calculator that it kind of looked like this, which, whoops, I was not supposed to cross the asymptote, does show me that this is a decay function that's been reflected, everything's been shifted up to, including the horizontal asymptote. So now I can see that my range is negative infinity up to 2 with a parenthesis, because the asymptote does not allow it to actually hit the function at negative 2. So simplifying expressions with exponents, we're going to go back to our exponent rules from when we were little kids. If I'm multiplying the bases, I keep that same base, and then I am supposed to add the exponents. So if I were to add these exponents together, 3x minus 1x is a 2x, negative 1 plus 4 is a plus 3. And there's nothing else you can do to that equation, or that expression, to simplify it. In this problem, when we divide bases, we keep the base, but we're supposed to subtract the exponents. But be careful that you're subtracting the entire expression. So x minus the quantity 1 minus x gives me a 2x minus 1 for my exponent. And then on number 10, we have different bases, but when you have a power raised to another power, the rule is we are supposed to multiply them. So 4 to the 3xz power over 5 to the 3yz power. Alright, number 11. We're going to solve an equation, and what these equations have in common is they either have the same base or they have a common baby base. So for instance, number 11, 5 to the 3x power equals 5 to the 4x minus 2 power. The only way for these equations to be equal is if their exponents were the same value. So I'm going to set up a smaller equation that says exactly that. I need my exponents to equal each other. So it looks to me like x must be equal to the number 2. Same idea here, x squared must equal 2x plus 3. This time I have a quadratic, so I'm going to use one of my many quadratic methods. I choose factoring. So x minus 3 times x plus 1 would be my factors for that quadratic. So my solutions are x equals 3 and x equals negative 1. Now we'll talk later about extraneous solutions. This is not a place where you need to worry about extraneous solutions just yet. Number 13, they do not have the same base. However, I think 9 can be rewritten so e is a 3. For instance, 9 is really 3 squared. So we have 3 squared raised to the x squared power equals 3 to the 3x minus 1 power. Now power taken to a power, we're supposed to multiply those together. So that's 2x squared. And now it's just like the previous problems. In order for these expressions to equate, I need their exponents to equate. So again, we have a quadratic. I'm going to need to use one of my many quadratic methods to solve it. Hope what factoring works, and I think it does. Yep. So I get x equals 1/2 and x equals 1, both of which will work just great. Now, similarly, here, if they have the same exponent, the only way for these expressions to equate is if the stuff on the inside is the same value. So 1 minus x must equal 2x minus 1. Oh, let's either be 3x equals 2, so x equals 2/3. This one's kind of interesting. Well, maybe. It's almost like a quadratic. So if I think of this as factors, like a 2x could equal 0, or e to the negative x could equal 0. X equals 0 is a good answer. E to the negative x, let's play with our calculator for a second. Well, actually, I don't think we even have to do that. We know that e to the negative x is really 1 over e to the x, so it's going to be a decay question. And what I'm asking you to do is realize where this function equals 0, or where it crosses the x-axis. And it never does. So the only way for this function to come out to 0 is if the x value is equal to 0. So it's kind of a boring question, sorry. And then here, we have a similar problem. I think we have a common factor of e to the x that I could take out, leaving me with x squared minus 5x equals 0. And e to the x, remember, is this time a growth. It's never going to equal 0, so never is my answer to this part. but x squared minus 5x could surely equal 0. If I factor an x out of that quadratic, I get two values. I get x equals 0 and x equals 5. Alright, number 17. Back to this baby base kind of a question. If I could rewrite these so they have the same base, then I'll be able to equate their exponents. Now, there's no way to write an 8 as a base 4. I think I need to think smaller and go to a 2. So 4 is really a 2 squared, and then 8 is really a 2 to the third. So this side of the equation is really 2 to the 2x minus 6 equals 2 to the third, and the only way for these expressions to equate is if 2x minus 6 is equal to 3. So 2x equals 9, and x equals 9 halves. 4.5 is acceptable. Number 18, the baby base that they have in common is a 3. So 27 is really 3 to the third. We'll clean this up in a minute. And then 9 is really 3 squared. So this really says 3 to the 3x plus 3 equals 3 squared. The only way for these expressions to equate is if their exponents are the same value. So 3x equals negative 1, and x equals negative 1/3. This kind of a question, when you have x raised to a rational exponent, the quickest way to rid yourself of that rational exponent is to raise it to the reciprocal rational exponent. Now, 3/4 power means that you are taking the 4th root of 81 and then raising it to the 3rd power. So remember, when we take even roots, we need to worry about both positive and negative answers. If you were to type 81 to the 3/4 power on your calculator, let's see, 81 to the 4th root is 3, I believe. And then 3 to the 3rd power is 27. 27 equals x, but it's actually positive and negative. 27 equals x. Okay, basic transformations. We've already discussed these today, but x minus 2 up in the x position. If you want to think of it as the general form x minus h plus k, where h and k are the horizontal and vertical shifts, this means that your function has transformed or shifted right 2 units. A plus 2 off to the side means that we have shifted up 2 units. And then the 2 in front is technically like a vertical stretch, but we're not going to worry about those for growth and decay functions. Instead, what I'm interested in thinking about here is the fact that we've got a negative and an x plus 3. Now the x plus 3 indeed shifts everything left 3 units, but when you have a negative in the exponent position, what actually happens is it changes it from a growth to a decay, but what's actually happening is it reflects the function over, this time it's going to reflect it over, oh goodness, the y-axis. So for instance, if you had a growth function at first, but then you had a negative exponent in the x position, it would reflect it this way to a decay, which reflects it over the y-axis. This formula is an oldie but a goodie, compound interest formula. If you ever see the words compounded monthly, compounded yearly, annually, daily, you're going to use this formula, where P is the amount that you invest, R is your rate written as a decimal, and N is the number of times that you collect interest each year. And then there is my favorite formula called PERT. PERT is where you compound continuously. So we can't give you an N for this question because continuously literally means every second of every day that you're collecting interest. So it's a continuous growth formula. We have an account that after 5 years, you invested $100, 12%. So we're going to do this problem annually, quarterly, and then later continuously. So let's start with the annually. That would be the blue formula. So $100. 1 plus 12% is 0.12, and then it said annually for this problem, so that meant 1 time. Now up in the exponent, that 1 shows up again, and then times t years, so times 5 years. Make sure you're using parentheses as I show. If you have the new math print, then just type it in like you normally would. I don't have a calculator, so I don't know what that comes out to. If we're going to do this same problem this time quarterly, this is money, so you want to round appropriately. The only thing that changes now is my n. The n is now quarterly, which means 4 times a year. So up in the exponent, that 4 shows up again times the 5 years. And then continuously is going to be my green formula. So PERT is $100 times E, the button E on your calculator, and then up in his exponent, 12% times 5 years. So whatever values these come out to on your calculator, good job. Okay, $4,000 is deposited into an account earning 10% quarterly, and then there's another account, 6% quarterly, $5,000, and then when will the one account be worth more than the other? I'm going to use my graphing calculator on my computer. I'm going to set up my equation for the first bank account into Y1 and the other guy into Y2. So we have $4,000, 10% quarterly. So 4,000, 1 plus 10% is 0.1, quarterly is 4, and then up in the exponent, that 4 shows up again, but this is the weird part. We don't know the time, so we're going to leave that as a variable. Now in the other bank account, it's 5,000, I believe, 6% quarterly. So eventually it will be worth more because it's got a higher interest rate. But our job is to figure out when eventually is. Or a lower interest rate. I don't know. The first one's going to be worth more. Sorry, I wasn't reading. Quarterly. And then up in the exponent, quarterly 4 shows up again, but I don't know the time. Okay. Now you have two places. You could look at your graph of the function. You want to get a good window, or else you could look at the table. I'm going to get a graph. So I'm going to go to my window. X, or T, represents number of years, so negative 10 is kind of stupid. I'm going to go 0, and I don't really know, so I'm going to start with 50. And then I'm just going to zoom fit, because my calculator tends to find a good window for intersections. What we're going to be looking for is where these two functions intersect. And if it doesn't show me anything good, then I'll change my window. Here's one. And I think they did intersect there. Let's see. So I can trace, and then chose 5, and then enter, enter, enter. Yep, looks like 5.7 years. They are going to be matching in value, and then after that, the other function takes over and creates more money. So roughly 5.7 years. A table would only give you answers that are between two integers, so you'd say between 5 and 6, or yeah, between 5 and 6 years. 25 and 26 in my textbook. Let's see. All right, I got 5 minutes to get this done. 331. So page 331, number 87. We have a couple who just had a new baby. They want to invest some money at 8.25% compounded daily, so that way they will have $40,000 in their bank account. So this is interesting because they actually gave us the answer of 40,000, and they don't tell you how much they invested. But they do tell me it's 8.25% and is compounded daily. So 0.0825 is my rate. Daily means 365. Don't worry about the quarter of a year. And then up in the exponent, they want the money to be ready when the kid is 17 years old. So 365 times 17. So for the sake of my time, what I would have you guys do is type this into your calculator, and it's going to be some number. It's going to be gross. So it's x times whatever that number is. And then to solve for x, you would just divide by whatever this number is. And that's going to tell you how much money they should invest off the bat so they can have that much money. And they want you to round to the nearest dollar. And then number 26, they want me to look at number 89 on that same page. So 5250 in an account that pays 11.38% compounded continuously, and how much money will we have after a various number of years. So because we're doing continuous, we're going to use PERT. And we're going to set it up for the first part. We're always investing 5250, so that's the P. And then up in the exponent, the rate is always 11.38, so 0.1138. For part A, they wanted it to be there for 6.25 years, so that's what I'm going to put for the time. And then when we get to B, it's 17 years, so very similar problem, just the t changes. So as long as you're careful typers with parentheses, that should be a very easy question. And I think that does it for 4.1.